So dear students, so far we have understood various aspects of Earth's atmosphere, various layers in the Earth's atmosphere, what is the reason for the existence of these different layers in the Earth's atmosphere, what is the primary chemical composition in each of these layers, how does it differ, and how does this chemical composition decide the observed variation of temperature with respect to height in these layers, things like that. Okay, so this picture just represents troposphere and stratosphere. So from this picture you can see that all the weather or all the weather phenomena generally take place in the troposphere, and only at times there may be some weather activity in the stratosphere. Okay. So today, in continuation with the last class discussion, which was about greenhouse gases and how is greenhouse effect demonstrated in the Earth's atmosphere, or in general how the atmospheric greenhouse gas effect is different from a greenhouse which is used for the plants or things like that. Okay. So in continuation to that discussion, what we will do is today we will try to understand what are the atmospheric windows. What are the atmospheric windows in terms of this window is in terms of radiation, let us say. Then after the atmospheric window discussion, we will try to understand what is the general circulation of atmosphere. General. Why does the circulation come into picture? Because we have a fluid system which is bound to the gravity of the earth, and this fluid system has a natural tendency to travel or to flow from one point to other point. That will lead to the idea of circulation. We will try to see how the basic or the very fundamental aspects of general circulation of the Earth's atmosphere. Okay, so then we will try to see how the seasons or these things are coming into picture for the Earth. Okay, now. So, like you see in the big picture is that the Earth's atmosphere spans over several hundreds of kilometers, and 99.9% of the Earth's atmospheric gas or by weight exist below 50 kilometer limit. Okay, so this picture shows many important things, like many important systems, like or many important aspects of Earth's atmosphere. So what you see is what we have discussed in detail is about this temperature variation, right? We have discussed this. So now in this figure, what you see several different types of clouds: stratocumulus or cirrus clouds, cumulonimbus clouds. So these are different types of clouds, and they generally develop at different altitudes in the atmosphere, and different set of physical processes are responsible for their formation, and at the same time each of these cloud is different in terms of the amount of moisture that it contains or the amount of precipitation that it can bring in, let us say. So because we will try to discuss several important aspects about the Earth's atmosphere in the entire course, it is important that where do these different aspects are found, I mean, in this big picture. Okay, so what you see is the commercial jets that we know generally, they fly at an altitude of 10 kilometers, and let us say, so the ozone layer is between 30 to 50 or 50 kilometers. So these are the very important terms that all of us must have heard about. Okay, and let us say the incoming meteors, we have already seen that the meteor ablation happens in the mesosphere. So this is the mesosphere. So whatever be the existing density in the atmosphere at mesospheric altitudes, there is still enough for burning a meteor. And weather balloons, so these balloons are the ones by which measurements are carried out. So different types of measurements are carried out, I mean using different methods and different equipment or different devices. Okay, so because we know it for a fact, I mean right now we know how does the atmospheric constituent vary with respect to height, but at any given point of time different types of experiments can be devised to understand or to quantify several physical parameters in the Earth's atmosphere. Okay. So, this is the big picture where you see so many other things apart from the things that we have discussed. Okay. Now, we talk about what is called as the atmospheric radiation, right. Now, so yesterday we have seen that it is mainly the infrared radiation which is trying to escape the Earth's atmosphere and which is originating the Earth, the solid Earth is being trapped by the carbon dioxide and other greenhouse gases. As a result, we see that the temperature of the planet Earth is significantly larger than what it should have been. But we have also learned that with the increase in the concentration of greenhouse gases, the greenhouse gases are generally quantified in ppm, parts per million. With the increase in these gas concentrations, the amount of heat that is to be trapped, which was otherwise being escaping to the space, the amount of heat that is being trapped is increased, and as a result we see that the average temperature is going up, and we call this as a global warming, right. Now, we will in these slides what we will do is we will try to see what are the different windows in which we can see the atmosphere, or what are the windows in which the atmosphere becomes transparent, what are the windows by which we can also probe the atmosphere, things like that. Okay. So, radiation is generally what we have defined in our earlier classes also is the mode of energy transfer. Radiation is nothing but the way in which energy transfer is taking place from one point to another point. So, energy transfer. So, and we have also seen in the very first few lectures that the radiation is the most effective in vacuum, in the absence of any medium, right. And the energy transfer is achieved by electromagnetic waves. Electromagnetic waves are the ones which will carry the energy from one point to another point. And it is the only mode to transfer energy without the presence of a substance, without the presence of any material or in general without the presence of any medium. That means even in absolute vacuum, this means of energy transfer is achievable and works better, or I mean the best in vacuum, empty space. Okay, so we can say that the radiation, but most importantly, the radiation is the only way in which the Earth receives the energy from the sun. There is no other way that we can receive the energy from the sun. Okay, and by far all the weather systems, everything that happens in the atmosphere, everything that happens in this gas blanket is powered by radiation. So, this incoming radiation, or 1340 watts of power that we get per unit area from the sun is what drives the entire atmosphere. It drives the weather systems, it drives every other thing. So, this is the basic aspect. Okay. Now, what we know is that from the sun and earth geometry, we know that there are spatial and temporal variations of there are spatial and temporal variations. That means, depending on the position of earth with respect to the sun. Sun is rotating, that is a different thing, but with respect to sun, treating sun as a stationary object, we treat earth to be revolving around the sun, and this revolution takes generally 1 year for completion, right. Now, so depending on the position of earth at different times, so you have variation in the position and variation in the time, in the temporal domain. So, depending on spatial and temporal positions, it is always possible that earth receives different amounts of energy at different points in space and time. Okay, so that means that the receipt of energy is different at different times. So, at the top of atmosphere, so we always take it at the top of atmosphere. So, we take that the earth is receiving energy at the top of atmosphere, and this energy travels down towards the earth's surface, and it creates all the effects. It creates ionosphere, it creates several ions, electrons, things like that. And we know that from the atmospheric composition itself, from the basic atmospheric composition itself, it is very important to study the amount of radiation at the surface. Okay. Now, what we have seen is that ozone, O3 molecule requires the ultraviolet radiation, The ultraviolet radiation is short wave. Why? It is short wave because the lambda is very small. The ultraviolet radiation's lambda is very, very small. Okay. The other molecules, let us say water vapor and carbon dioxide, these molecules they generally are excited by the infrared radiation. So, what the most important thing is ultraviolet radiation dissociates ozone, that is what we have seen, and infrared radiation. So, these two molecules have the vibrational bands in the infrared spectrum. So, since infrared spectrum has longer wavelengths, I mean several orders of, let us say, up to meters. So, we call this as long wave radiation. So, now the radiation is now categorized into basic categories such as short wave and long wave. Long wave radiation are of importance for water vapor or water molecule and carbon dioxide molecule. So, now we need to consider different types of radiation. So, let us see how many different types of radiation can we get from the standard solar spectrum. Okay. Now, you see Earth Sun geometry, if you see how the Earth is aligned or kept in position with respect to the Sun, we know that Sun is holding Earth by gravity, and it's like it is revolving around itself and it's also revolving around the Sun. Now, you have an axial tilt. I mean the north-south axis is not completely perpendicular to the Sun. So, it has an axial tilt. Okay. In addition to that, let us say you have Sun here, unequal areas of surface receive equal amounts of energy. Okay. So, any given point, now you break it to the point, any given point on the Earth receives different amounts of energy as a function of time. Okay. Now, Earth is revolving around itself from west to east, right. So, as a result, what you see is, if you are standing on the North Pole, you will see that the Earth is revolving in counterclockwise direction, and if you are standing on the South Pole, you will see that the Earth is revolving around itself in the clockwise direction. Okay. These things will be essential for understanding how the seasons come into picture, things like that. Okay. Now, you see seasons. I mean, if you imagine an elliptical orbit, what you will realize is that, so this axial tilt that I was telling is about 23.5 degrees. Okay, so that is why you have the tropics between plus 23.5 and minus 23.5 or 23.5 north to 23.5 south. Okay. Now, so as the Earth revolves around the Sun, we have different seasons. Let us say we have seasons in terms of spring, winter, summer and autumn. And there are times in which the Earth is in such a position that the amount of the duration of day and the duration of night are exactly equal. Okay, there are some times like that, and those times are generally called as the equinoctial times. Okay. Now, so it's basically the rotation of the Earth combined with the axial tilt gives you the seasons. What happens is, so if you if you imagine the Earth, which is kind of, so this is the pole, the circle. So this is the north-south axis, and this is the perpendicular axis with respect to the ecliptic plane. You will realize that at some points in the time, the entire north pole will be in a position as if it is facing away from the Sun. So this period of time is winter, and when it is exactly in the opposite direction, due to the axial tilt, you will see the Earth to be in this way, where if this is the position of the Sun, this is the summer for the North Pole. So due to this combined relation, we can say that seasons do originate for the different positions on the Sun, on the Earth. Right. Now, let us say the basic definition of radiation, the radiation spectrum is the distribution of radiative energy over different wavelengths or over the complete wavelength spectrum or frequencies. In meteorology, in the atmospheric or in this area of study, not the entire part of the electromagnetic spectrum is of interest. It is only a small part of it is of interest for us. Okay. Now, there are three important ranges in this electromagnetic spectrum. One, the ultraviolet radiation, that means the lowest wavelength part, the visible radiation, let us say 3500 to 7000 nanometers, 7000 angstroms, and the infrared radiation, which is the highest wavelength part. Okay. Now, if you see the radiation in the Earth atmospheric system, let us say you have ultraviolet radiation, visible radiation, infrared radiation. Okay. Now, the wavelengths are typically for the ultraviolet radiation, it is 10 to the power of minus 2 to 0.4 micrometers. So, this is ultraviolet radiation. You have the extreme ultraviolet radiation in this, and you also have the ultraviolet radiation, which is going to be touching the boundary of the visible spectrum. Then you have the visible radiation, which is 0.4 to 0.7 micrometers, and the infrared radiation extends very far, and the infrared radiation is 0.7 to 100 micrometers. So, what is the physical effect that you see of this radiation? I mean, if you see the white light that is coming from the sun, it contains the entire, all the three different ranges of wavelengths in it, and the effect that you see of this different parts of radiation is the sunburn. If you experience ultraviolet radiation, which you may have never, you will realize it will cause you sunburn. Visible radiation is the sunlight that you see with your naked eye, and visible radiation has again different colors, which you know already. And infrared radiation, like I always say, infrared radiation is the heat radiation. The feeling that you have, the hotness that you have is basically caused by the infrared radiation, and infrared radiation is again categorized into near infrared and far infrared. So, by all means, these ranges are defined for the purposes of discussion in the Earth's atmospheric system. Okay. Now, if you categorize them into classes, let us say the entire range up till 1.5 micrometers is called as the short wave radiation, and long wave radiation is anything which is above 1.5 micrometers. So, this is short wave radiation and this is the long wave radiation. Okay, now, if you put if you consider the entire energy that is emitted from the sun, let us say you take the entire solar spectrum, you integrate, then you will get what is the total energy, and then you calculate percentages of these spectral windows. Let us say how many windows you have 3 windows. Let us say the ultraviolet window is the one, the visible radiation window is the second one, and the third one is the infrared radiation. So, you calculate the weights for these 3 windows in the entire solar spectrum. You will realize that the ultraviolet radiation is nearly 7% of the entire energy that is emitted from the sun, and the visible radiation is nearly 43% of the entire energy, which is almost like 50% of the energy that is emitted from the sun, or the yellow disk that you see is visible. 50% of it is visible, and the infrared radiation, in the near infrared it is nearly 37%, and in the far infrared it is 11%. Right. And now, what is important is, let us say this is the sun output is taken at, let us say 6000 Kelvin, right, 6000 Kelvin, whatever that you get, because in between you have vacuum, so there is no such thing as which can absorb the radiation and can attenuate the incoming radiation, right. Now, like I say, Earth is also to be considered as a black body. Black body as such, it is a black body at let us say 255 Kelvin. So, if you take the Earth to be a black body, the amount of radiation that comes out of Earth is entirely in the long wave radiation, that is 100% in the long wave radiation, that too in the far infrared spectrum. That means, whatever the amount of radiation that Earth radiates is above 1.5 micrometers. So, now you have defined two types of radiation, one short wave radiation and one long wave radiation. When you are talking about the sun, both the windows, both the limits are equally important, short wave radiation, is important and long wave radiation is also important. Short wave radiation, some of the short wave radiation is absorbed in the atmosphere like ultraviolet for causing many chemical effects, let us say, and some of the radiation, let us say the visible radiation, which is nearly 43%, doesn't contribute to any effects. I mean, this is not energetic, so it will not dissociate or ionize anything. It will be directly reaching the surface of the earth. And the third part is the long wave radiation, right. Now, when you take the same example for the earth, what will happen is earth will completely radiate or give its energy only in the form of infrared radiation. Okay. Okay. So, this is the short wave and long wave radiation. So, solar radiation is short wave radiation, incoming radiation. Terrestrial radiation, that is the radiation emitted by the earth, is completely long wave radiation. Okay. Now absorption, how does this radiation gets absorbed? Absorption is basically the concept of conversion of radiation to heat. When you keep some object in the place in the path of the radiation, this radiation will be absorbed by this object. Now, what will be the effect of absorbing this radiation? This object's temperature will go up. Okay. So, rise the temperature of the absorbing substance, that is it. This is the effect. So, what is happening? The energy transfer or energy conversion is from radiation, that means electromagnetic waves, to heat, right. So, this is the effect. Now, from the well known Kirchhoff law, we can say that if a substance is an efficient emitter in a given wavelength range, it is also an efficient absorber at the same wavelength range. So, it is like the concept of black body. Black body radiates the entire spectrum. All the wavelengths are emitted by the black body if you heat it to a particular temperature. And at the same time, if the black body is capable of emitting some radiation, it is equally capable of absorbing the same radiation if it is incident on it. Okay, so, the absorption and emission will happen at the same wavelength range. If a body is capable of emitting certain wavelength range, it is also capable of absorbing the same wavelength. Now, we talk about what is called as selective absorption. So, the absorptivity of atmospheric gases are highly specific to certain spectral bands or wavelength ranges. That means, you consider N2, you consider O2, you consider O, you consider nitric oxide, you consider CO2, you consider H2O. These are different species which are present in the atmosphere. I mean, to different concentrations, of course, but if you allow radiation to fall on these gases, so the radiation has, let us say, a limit of 0.1 to 10 to the power of 6 nanometers. The incident radiation window is from 0.1 to 10 to the power of 6 nanometers. What selective absorption means is that each molecule or each species will absorb in a particular very narrow wavelength range. This is called as the selective absorption. Okay. Now, solar radiation, let us say the earth is emitting the infrared radiation into the atmosphere, the sun is emitting both the short wave and long wave radiation into the atmosphere, right. So, both of them have effects. I mean, the infrared radiation emitted from the earth has some effects, and the entire wavelength range that is emitted by the sun also has some effects. So, solar radiation, short wave radiation, let us say, UV absorbers are ozone and oxygen. So, ozone and oxygen have the ability to absorb UVA, UVB. Visible range, nothing absorbs. So, that means it is a window where visible radiation is not absorbed by any gas. So, why? I mean, it's a very spectroscopically it is a very easy answer, because visible radiation does not have the amount of energy to excite electronic vibration states, right. Now, terrestrial radiation, the radiation that is emitted by the earth, is long wave radiation. So, IR absorbers. So, these molecules have the ability to absorb the infrared radiation. These molecules are generally called as the greenhouse gases. At the peak terrestrial radiation that we have seen in the last slide, 8 to 12 micrometers, almost none. I mean, this wavelength range is not absorbed by any gas, and this is again a window. What I am calling is a particular value of lambda, a particular range of lambda for which the atmosphere is transparent. So, if I shine visible radiation in the atmosphere, nothing is absorbing. It will, the entire atmosphere is like a transparent glass which is not absorbing anything totally. And it is also the same thing for, let us say, this peak terrestrial radiation 8 to 12 micrometers is the wavelength range which is not absorbed by any greenhouse gases the least. Okay. So, what you can say is the atmosphere is transparent for solar radiation over a particular wavelength ranges. You call these wavelength ranges as windows. Okay. Now, the atmosphere is transparent for solar radiation only over a particular wavelength range, but nearly opaque for terrestrial radiation, greenhouse gas radiation. So, this is what we have already talked about, right. So, atmosphere is transparent for solar radiation, but it is nearly opaque for terrestrial radiation. So, long wave radiation is, even though if it is trying to go away into the space, the atmosphere is a trap, the atmosphere is opaque. So, the atmosphere will not allow it. Okay. Now, if you see the global long wave balance, how much amount of energy is emitted, how much is reflected, how much is transmitted, things like that. So, what you see is 30% of the solar radiation is reflected by the clouds. We have already seen that clouds have a very high albedo and they reflect more, they reflect much radiation that falls on it. So, to put a number, 30% of the solar radiation is reflected by clouds and atmospheric gases and the surface. So, if you have 100 photons coming onto the earth, 30 of them are reflected by the clouds, by the gases and by the surface. 25% of the solar radiation is absorbed by the atmosphere. So, this what is being absorbed. So, naturally if the radiation is absorbed by the atmospheric temperature will increase, and this temperature increase will create a pressure gradient, and this pressure gradient will create winds, patterns of winds and circulation and so many things. So, it is basically this temperature change that is caused by absorbing radiation is what drives the weather. We already kind of seen this, right. Now, the remaining 45% of solar radiation is absorbed by the surface, okay, by the surface, oceans and the land surface oceans or ocean cover, ice cover, whatever it is. So, now just look at it. I mean, what I really want to emphasize here is that, so of the radiation that is entering the that is incident on the top of the atmosphere, 30% is lost then and there itself. 25% of the 25% of solar radiation heats up the atmosphere. That means it will increase the temperature of the atmosphere. Okay. Now, the remaining 45% of the solar radiation is absorbed by the surface. So, surface also gets heated up, right. Surface, anything that absorbs radiation will get heated up. So, surface temperature increase is caused by this 45%, atmospheric temperature increase is caused by this 25%, as simple. Okay. Now, there are several small systems in the global atmospheric system. Let us say influence of clouds on shortwave radiation balance. Now, see, I am saying that shortwave radiation is very important for atmosphere because it is what creates the electrons and ions. Okay. But what happens is clouds and things like that will change this equilibrium. Let us say if you have no clouds, clear conditions, if you do not have any clouds, of whatever the percentage that we have seen before, 70% of the solar radiation is absorbed by the surface directly, 55% direct and 15% diffuse by sky radiation if there are no clouds. So, whatever is coming is directly incident, and only 13% of the solar radiation is reflected. It is a very small percentage which is getting reflected. And if there are clouds, if there is an overcast, and 25%, that means these percentages change. 25% of solar radiation is absorbed by the surface because clouds are reflecting much, and of which 4% is direct and 21% diffuse sky radiation. Okay. Now, 51% of the solar radiation is getting reflected. Now, this reflecting percentages, these percentages are changing. Why? Because here you see 13% of solar radiation is reflected and 51% of solar radiation is reflected. So, this increase between 13 to 51% is only because of the clouds and the high albedo that the clouds possess or the cloud tops possess. So, in let us say in totality, what you can say is, so you define a window as something that lets light or the radiation to pass through, just like windows. what we have in our room. So, windows are the ones which will allow light to pass through into the room, right. Atmospheric window is a spectral range where the atmosphere is nearly transparent. Atmospheric window is simply defined as a spectral range over which the atmosphere is nearly transparent. So, atmosphere is allowing the radiation to reach the surface. Okay, there are two atmospheric windows: visible range window, which lets most of the solar radiation to the surface, right, 43%, enables solar radiation to deliver the bulk of its energy to the surface for use in climate processes, yes. Then the long wave window is between 8 to 12 micrometers. Again, we have seen that the greenhouse gases also do not utilize this energy, the 8 to 12 micrometers wavelength energy. That means the gas is, of course, the other gases do not have any business with this very low energy spectral band, and this radiation passes right through the atmosphere and enables to Earth to vent off some of its energy back to the space. Now, had the greenhouse gases, if they had the ability to take this energy also, what would happen? The average temperature of the Earth will rise incredibly, and had the let us say, so that is why, so this window, the long wave window is helpful for losing some temperature, some energy away from the Earth. So, where does this radiation go? This simply escapes to the space. So, if you have a filter somewhere in the distant, let us say, galaxy, and if you see Earth in this spectral window, you will see a very clear image, because much of it is escaping the Earth, right. So, the terrestrial radiation has a window in this range, and the visible range window is in this range. So, this allows the sun to deliver energy onto the surface, which with this radiation heats up the surface, and this radiation kind of allows the surface to lose some temperature. Okay. So, these two windows are very important. Okay. Now, so this was something about the atmospheric windows. What is the purpose of these windows? How do these windows contribute to the formation of weather or climate, things like that. Okay. Now we talk about another very important aspect of the atmosphere, or we will not talk about it in a very detailed way. We will cover it or with a small introduction. Okay. Now we call it as atmospheric circulation. So what is circulation? Circulation is just a cyclic process in which things will come back to its origin and it will go on again and again, right. Atmospheric motion or wind exhibits a range of horizontal scales. So before we talk about circulation, we talk about scales. So what is a scale? Let us say, how do you define a scale? A scale of motion in this context, let us say, scale of motion. So let us say, if you consider a typical human being, and if I ask you what is the horizontal scale which a human being can cover in a particular day, you would say, let us say, a few kilometers, let us say 20 kilometers, 30 kilometers. So the human being has the ability, so it will not go beyond few kilometers, few tens of kilometers. So let us say, if you extend this example, what you can realize is that molecular scale motions, let us say, if you consider gas and if you consider molecules in it to be moving from one point to other point, how much distance do you think they will move? How much distance they will travel? This is defined as the scale of a motion. So it can be very large, it can be very small. So since the molecules are very small, the typical scale of molecular motion will be much less than, will never be greater than 2 millimeters. So all the molecular motions and all the mean free paths that you define are always below this 2 millimeter limit, right. So now the scale can go as low as nanometers or even lower than that, but the scale on the other side will go into a very larger numbers. Now in atmospheric science, the most important thing is we generally talk about systems, or we generally talk about things or stuff that we see with our naked eye. That means we are generally not bothered what happens at the molecular level, what happens at the micro level. We see things in a macroscopic description. That means we see winds to be moving from one point to another point. I mean, we see what the effects that wind will do when it moves from one point to other point. We see clouds to be moving from one point to other point. That means the physical description that is needed is macroscopic in nature. It's not, we don't see what is going on inside. We will see how does the system exhibit itself from the outside for the perception of a naked eye. Now, the system here is beyond a naked eye. I mean, the systems are far too big to be able to comprehend by a human being, right. Now, even in itself we have different scales of motion. So, the scale of motion is the dimension, is the length dimension over which a physical phenomena or an atmospheric phenomena can exist or can occur. Okay. Now, you define these scales into 4 different types. Micro scale are the systems which span over the distances of few millimeters to at least 2 kilometers. So, what are the examples for eddy currents? Swirling motions of air. That means you see small swirling motions of air which will not be very large. They will not be more than 2 kilometers if you measure. So, micro scale motions are the ones which are very small in size, in horizontal scale. I mean, you say the length scale. That is a very easy way to understand. So, you always, it is just the unit of length. Okay. Mesoscale is anything which spans from 2 kilometers to 2000 kilometers. It is a very large scale. So, for example, waves with horizontal dimensions of the order of tens to hundreds of kilometers. There are global atmospheric waves which exist over several hundreds of kilometers. That means the length scale of wave, the wavelength of this particular wave will be of the order of several hundreds of kilometers. But it is a wave which is traveling from one point to other point. So, for example, mountain lee waves, thunderstorms, things like that. So, these the motions which are from the order of 2 kilometers to 2000 kilometers are categorized into mesoscale motions. The synoptic scale is a more important or more familiar scale of motion in which many of the atmospheric processes happen, and also many of the people, many of the scientists, much of the science is going on. So, synoptic scale is the motion which covers almost like a wide range of scales, 500 to 10,000 kilometers. So, waves with horizontal dimensions of the order of several hundreds of kilometers. So, for example, high pressure, low pressure systems. So, if you see any weather system or any weather map even in your news broadcast, you will be able to realize that entire, let us say sometimes an entire country can be a high pressure system, and it will be surrounded by a low pressure system. That means these systems are spanning over several hundreds of kilometers. So, and the last scale of motion is planetary scale. So, which is the broadest feature of the all, and the planetary scale system, like the name itself suggests, planetary scale system is of the scale of the planet itself. Okay. So, features with horizontal dimensions comparable to the size of continents or oceans or to the planet itself are covered in this particular scale. Okay. So, it is micro scale, which is kind of small, mesoscale, synoptic scale, and planetary scale. So, these scales of motions are very important. Whenever you pick up a system, it is very important for you to categorize this particular system into one of these scales and then use the techniques accordingly. Okay. Now, atmospheric circulation. So, what is atmospheric circulation? Earth's atmospheric circulation, Earth's atmosphere is not static. It's a dynamic thing. I mean, it doesn't stay still. So, winds and storms are regular features on this and other planets. So, it's atmospheric circulation. An example that atmosphere is not static is that there are winds and storms which are regular features that you see in the atmosphere. Okay. So, what is the reason for the circulation of the atmosphere. Why should the Earth's atmosphere move from one point to another point? It's a fluid system. Nothing can stop a fluid system from moving from one point to another point. Anyway, as the sun warms the surface on the Earth, it warms the layer of the air that is directly above the surface. Now, we specifically know what is the radiation, which part of the radiation is the one which reaches the Earth's surface and increases its temperature. Right. Now, what I am trying to say here is, as the temperature of the Earth's surface is increased, the layer of air that is immediately above this surface is naturally getting heated. Right. It naturally gets warm. What happens? Warm air has a tendency, if you take warm air in a parcel, this will expand, right? This will expand, and as a result of expansion, the density will go down. If the temperature is going up, the density will go down, and if the density is low, anything which is less denser will try to move up due to the buoyancy. So therefore, it rises. Yeah. So we have learned something about atmospheric scales of motion and various types of weather systems or atmospheric systems, which will be categorized as these scales. Now, in tomorrow's lecture, we will try to understand the atmospheric circulation and various aspects of atmospheric circulation. Yeah, thank you.